Christian is our speaker today. He is a graduate research assistant at the University of Texas at Austin. He is co-advised by Tom Edgar and Michael Baldea. And he's going to be talking today about meters to models using smart meter data to predict and control home energy use. And, Christian, I'll just start with a little bit of an introduction. He graduated from Brigham Young University 2 years ago and entered UT Austin. And, Christian actually got to work, I got the opportunity to work with Christian for just a little bit while he was here at BYU, and he certainly had a great impact here. At UT Austin, he has been the recipient of a National Science Foundation graduate research fellowship. It's very competitive and certainly well-deserved for Christian. He actually is with his work on smart grids and residential energy use, Christian has also achieved some international recognition for this, and is actually going to be going to work in the Netherlands this summer, or I guess this fall. Is that right, Christian? You're going to be going there this fall? So he's going to be going there this fall to work with two universities in the Netherlands, the University of Delft and the University of Twente. And anyway, so he's going to be working with researchers there to transfer some of the things they've learned from the UT Austin Smart Grid Energy Demonstration Project. And so with that, I'm going to go ahead and, let's see, is there anything else I missed there? I think I covered it all. So let me go ahead and turn it over to Christian now. I'm going to go ahead and make you the presenter, Christian, and then if you can just click share my desktop, then we should be able to see your desktop. And just as Christian is going, just recall that this is, if you have questions as we go, feel free to put it into the chat window or to interrupt our speaker at any point. If we need to have a discussion or clarify points as we go, or tangential issues that we'd like to cover, feel free to do so. We can have more of a discussion than a presentation here. So with that, I'll go ahead and turn it over to Christian, and we'll just I just ask that you keep your microphones muted as he's presenting, and then if you have a question or a comment, feel free to unmute, or like I said, feel free to use the chat window. I'll keep an eye on that, and then Christian, I'll ask any questions that come through that chat window. All right, Christian, go ahead.
All right, perfect. Thank you again, Dr. Hendren, for allowing me to participate in this. I haven't always been able to participate live, but I usually go back on YouTube and watch some of the presentations that have been presented. So today I'm going to be speaking about meters to models using smart meter data to predict and control home energy use. And this is a very relevant topic, I think, with all the access to smart meter data becoming more readily available and more smart meters becoming installed. So leveraging this in the best way is one of the interests of research here at UT Austin. Like was said, I'm advised by Dr. Baldea and Edgar, and a lot of this work has been in collaboration with Wesley Cole, who just graduated from here. So to just give an outline of what's going to happen, first I'm going to speak about the role of residential energy in the peak power challenge. And from there, I'll talk about how we can use smart meter data to create reduced order or simplified models. And then using those models, use control and optimization strategies such as model predictive control to find ways to mitigate the peak power problem. And then along with that, I'll show some of the simulation results that I've had here. So to just give a broad perspective of energy within the United States, so of the 100 quads of energy, primary energy that the U.S. uses, about 40% can be attributed to buildings. Of that energy use, about half of it is residential, half of it is commercial. But if we were to look specifically at one load on the electric grid, just heating and cooling in particular, that amounts overall to about 50% of total energy consumption, which is a significant portion of the amount of energy that's used in the United States. And so if that wasn't, sorry, is that a question? Okay.
No, that was just somebody joining. Go ahead.
All right, now I know what that means. Okay, so if the size of the load itself was not of concern, then consider like, especially climate-wise, the amount of energy that's contributed, it comes from HVAC. So like here in Austin, where cooling is a primary load, about 45% of electricity energy use in a typical Austin home can be attributed to heating and cooling. So while heating can be met by like a natural gas furnace of some sort, cooling is primarily an electric load through a single direct expansion HVAC system. So the problem with this load in particular, the cooling load, is that it's highly dependent on a number of factors, which are human behaviors like preferences in terms of your thermostat inside of your home, as well as obviously the weather outside. And so it's like a highly variable load. And what that does is it creates a shortage of supply later in the day. So that's what's referred to as the peak power problem. And so you can see, so this is just for one day in June. You can see that the energy demand fluctuates throughout the day. So as people get home, they all turn on their air conditioning system, their TVs, they do their laundry. And so during this period, this very short period here, you have increase in demand, which means that that power has to be supplied some way. So a lot of times that comes from peak power plants, which just work during peak times. And so that's a lot of money to build them, and they only run for fractions of a year. And so during that time, it's really expensive. You can see this curve here. It gets really expensive for utilities to provide that power. And so when there's a shortage, then that's when you start to get brownouts or blackouts, which causes a lot of disruptions to the grid and economical problems. So the reason that we know that residential energy is such a big contributor to this point here is through a lot of studies that have been done. So here is an example. This is from Dallas, and this is, so on the left is a moderate day, like spring day, and on the right is a peak day. And so you can see that, so on the y-axis is power demand. So you can see that for the industrial and commercial sectors, the increase in power consumption is pretty marginal compared to the large factor that residential energy increases. So that's about 5 times as much, and that's during 1 hour of the day. So meeting that load can be very difficult. So the way that we propose to solve this problem is through the use of smart meter data. So the idea is if you can use energy storage within a home, use the inherent thermal mass within a home, and then apply some smart controls, then you can leverage the thermal mass within homes for pre-cooling, and you can find ways to stagger or shift and lower the peak load. So you spread out that load instead of having it all concentrated at one point in time. So the way that we'll do this is first, we will be pulling electric energy from smart meter data, and then from there creating models and then using some optimization schemes to be able to show how we can leverage that thermal mass. And so there is a lot of incentive, especially on the utility side. Back in February of this year, Con Edison, which is an electric utility up in New York, announced that it would give about $2,600 per kilowatt of peak shifting using thermal energy storage. So they were willing to give that size of subsidy. And then they were also offering, like just for batteries, to give a $2,100 per kilowatt hour incentive just to shift that peak load off. So there's a lot of incentive on the utility side to be able to find strategies to shift that load. It's a lot cheaper for them to pay a bunch of customers some money to participate in a program or to use some sort of thermal energy storage than it is for them to build a new power plant. So, so in order to be able to control and be able to use the thermal mass, we need to be able to model the homes. And so the problem is that homes are very complicated. So just for an example, so for a single air node within a home, you can see all the contributing factors that can go into just changing the temperature at that one air node. And so imagine having to do that for the entire home. So current building simulation tools such as Energy Plus and eQuest are able to represent a thermodynamic model of homes But the problem is that they require a lot of details to be able to accurately describe both the behaviors and efficiencies inherent in an actual home. And anyone familiar with the software knows that it requires a lot of training and understanding to be able to really model a home. And so maybe you can model one home accurately, but the problem is when you try and scale that out to the size of a neighborhood and to be able to shift the load of an entire neighborhood. So this is an example of some results from smart meter data that our lab has done. And so on the x-axis, this is the average outside air temperature in degrees Fahrenheit, and over here is the average AC energy. And so while if you had an accurate model, you might be able to scale it out by maybe multiplying it by a factor. At lower temperatures, you can see that the spread is lower, but as you start to get into high temperatures, when you would actually experience peak power, you start to see a spread in energy behavior. So your model will become less accurate when you need it to be more accurate. So using information from actual homes is a lot more useful than trying to develop a lot of models from complicated software. The idea behind this is if you can use the historical smart meter data to be able to capture the behaviors and house properties so that you could create some sort of house model that would be able to capture that. And so the way that we're going to do that is through a reduced order model. Reduced order models are low-dimensional approximations of more complex models that reduce the number of variables to those that have the most impact. So reduced order models, or ROMs, are used in controls optimization to reduce the computational intensity when real-time solutions are needed. So a lot of model reduction techniques have been used in building models, and we'll show you the form of the model that we came up with using smart meter data. But so just to give an overall picture of what we're going to do is that we will be using we'll be getting AC energy use from smart meter data. We'll be using thermostat settings from smart thermostats and audit data, as well as outdoor temperature. From there, we'll be able to regress the model parameters for a model that will use the inputs of outdoor air temperature and thermostat set point to be able to predict energy consumption within a home. As was stated earlier, Austin has a smart grid demonstration project here. Here it's called the Pecan Street Research Institute, or Pecan Street Inc. And it has over 300 homes outfitted with smart meters, as well as a number of other, it's a very next generation neighborhood. We're going to be using information from these newer green built homes to be able to evaluate AC control strategies. So one of the things that we had to develop in order to do this is to be able to pull out actual information on AC energy use. And that was done through a technique called non-intrusive load monitoring, which is a way, non-intrusive load monitoring is a way of using, being able to pull out information from data to be able to extract it. And so the way that it works, it's called non-intrusive because the non-intrusive characteristic stems from the standalone nature of the method, so you don't have to install any more tools. And then the load monitoring means loads of appliances are disaggregated or separated from the overall energy use.
So Christian, just had a question about this. Could you explain this? Is this for a typical home, or what is this load profile here?
So I just wanted, this is an example of smart meter data. So on the x-axis here, so this is for 1 day, and so you can, and then over here is the energy consumption. So you can see something is cycling on and off here, and it's pretty large in comparison to everything else. And then something is going on and off throughout the day, and then the large load again. So some of these homes have been sub-metered to measure actually like the AC energy use. So this is the actual measured AC energy use going on throughout the day. So while here this is the AC cycling on and off because of the thermostat, down here might be like your refrigeration cycle is going on or off. So the technique that the non-intrusive load monitoring technique that we use use the fact that there's a period of the day where AC energy use is a dominant load. So if you can detect that on and off signals during some sort of training period, then you can be able to identify what kind of pattern is required to say the AC just switched on and switched off. And so from there you can disaggregate or estimate how much energy use was used for AC energy use. So this is important to be able to, so that we actually understand how AC energy is changing throughout the day, which was not possible before smart meters were installed, because there wasn't this kind of data available. So we were able to show that using 1 or 5 minute data was discrete enough that you could be able to actually pull out that energy on AC energy use, whereas longer times you're not able to do that as successfully. So now we have access to the data in real time, and we also have access to weather data and the thermostat data. So now we move on to the actual modeling. So this is the form of the reduced order model. This is an autoregressive with exogenous inputs model, or an ARX model, which means that it uses information from previous time steps to make estimates for the next time step. So in this formulation, Y stands for the electricity use, dBT is the dry bulb temperature, and C is the thermostat set point. And then these model parameters A, B, C, and D are just parameters for the model. So we'll have access to 41 homes of complete data for 2 months worth, and so we'll use a portion of this data to regress the model parameters, and then we'll use the rest for validation purposes. So an example of one of the reduced order models is shown here. So in this, this is time on the x-axis. Here we have the outdoor dry bulb temperature and the thermostat set point, and then the energy in kilowatt hours, where the blue is the actual and the green is the estimated. So you can see that the model, or the estimation of energy from the reduced order model is able to follow the overall trend of the actual data, although times when there's like large jumps in electricity use, or maybe like zero-sum electricity use, we don't always capture. However, the R-squared value for this sample house, for example, is 0.752, which is about the average which is near the average for all the homes. So although it's not completely perfect, it is accurate enough to be able to use in some sort of control scheme. And so especially, so this is the hourly interval, but especially at like the daily interval, the model overall is accurate. So now we're going to go into the actual control strategy that was implemented. So the idea is to be able to use the building thermal mass to be able to store energy. So there are other examples of thermal energy storage. For example, chilled water tanks, or like ice storage, where you use electricity. The idea is that you use electricity when it's more abundant or cheaper to produce, and then so that later on you can reuse that energy. So in terms of buildings, it's free, so you don't have to install an additional tank on the side of your house of some sort, but it does require intelligent operation. So it's not something that will necessarily be intuitive. So optimization is the best way to be able to employ thermal energy storage. So, but there are some challenges. For example, you're using just the building envelope. So depending on the efficiency of the home, whether or not heat is leaking out of it or not, you might have small capacity. There's also more integration, especially when considering different houses. In terms of each house is going to have some sort of thermal preferences. So what do the owners of the house actually tolerate in terms of temperature? And then you also have the fact that each house is different. So to show an overall scheme of how the controls will go, is that so this is an overall diagram. So the inputs to the model, or the inputs to this control scheme, will be the weather. And in the center, we'll be using a centralized controller using model predictive control, which will be looking ahead at the next 11 hours, making decisions moving forward. This is a centralized control, which means that the controller will be able to communicate with each house and make the best decisions to be able to lower the overall peak for the entire grouping of homes. And so the challenge here is that it would require, if this were to be actually implemented, it would require some sort of information sharing. So there would have to be some way for each house to communicate with the centralized control and be able to communicate back. But for the purposes of the study, we're going to consider the benefit of having some sort of centralized control, maybe by like the utilities. So the formation of the control is shown here. So in our model predictive controller, we're going to be looking, the time horizon is going to be 11 hours looking forward. So the goal will be to minimize the overall peak, the largest peak throughout the day through adjusting the thermostat set point. And so the constraints on that are that we do want to lower the overall peak throughout the day. We'll be using the reduced order model that we found, that we individualized for each home earlier. This is the reduced order model here. And then we have some other constraints. First is some equipment constraints in terms of how much energy can actually be used by an air conditioning unit. And the second is comfort constraints that will be explained later. But these are the thermal comfort bounds that each home has specified for themselves. All right, so this is the overall control scheme. This is the overall model predictive control scheme. So to show an example of the boundary constraints we have here. So the upper and lower bounds for each house were found by using thermostat set point data from each actual home, as well as some audit data. So the lower bound for each individual house was found by identifying the minimum set point throughout the entire data set for that house. This value is assumed to be the lower bound for the users in terms of thermal comfort. The upper bound was given 2 values depending on the time of day. So during typical workday hours, so from 8 until about 5, houses were assumed to be unoccupied. The reason for this is that from the data set itself, it was unclear as to which houses were actually occupied and not during work hours. So the same assumption was just made for all the homes. But I think accuracy could be increased if maybe more housing survey data was available. However, so during unoccupied hours, the bounds in terms of thermal comfort was a little bit larger, but during the actual occupancy hours, the maximum set point was set as the maximum set point of the house, or sorry, excuse me. This upper bound here was chosen as 4 degrees Fahrenheit above the lower bound, and that came from typical survey data that says that that's the typical range for most houses. But if their upper bound during the unoccupied hours was lower than that, then that was set as the bound for the entire day. So if there's some house that is very strictly between 76 and 78, for example, that would just be their bounds for the entire day. So this is the constraints. So we then perform the optimization on the neighborhood. An example of that is seen here. So this was the control strategy that was chosen for this home for this day. So you can see, so early in the morning, it's operating at the upper bound, and then the controller decided to lower the thermostat. So at this point, the count is pre-cooling. So the electricity is more abundant here, and it will also be able to reduce the peak later. So during this time, the house is pre-cooling, and then later on, during typically peak hours, the thermostat is raised again by the controller. And so during these peak hours here, the thermostat has been raised, so the electricity usage is lower during this time for this house. So the controller used the thermal mass of this building to be able to store energy, and then so that they could delay when they turn the thermostat back on. So now over here it's operating again at constraint. So the HVAC system may actually kick on around here during an off-peak hour of maybe a different house. So the benefit of this is that each home will be operated differently in terms of how long do they pre-cool and how long and when do they change the thermostat set point, so that we can actually offset each of the houses. And so the advantages of that can be seen in the following figure. So this is an example of the control strategy for the 41 homes for just one day. So this is time down here. This is the outdoor air temperature, and over here is power. So to just explain, this dark blue line here is the base case. So that's what the homes actually did, according to their smart meter data. And then this example of this dotted line is the min peak case from our control scheme. And so the advantage of this centralized controller is that it's able to leverage the passive thermal energy storage of each house by pre-cooling each house on a different operation schedule. So that means that maybe houses that have thinner thermal envelopes or tight thermostat constraints can still run during peak times, while those with maybe large thermal envelopes or large thermal comfort bounds can slowly heat up. So in both cases, the thermal comfort bounds with each house are not violated, but you're still able to leverage the thermal mass of each home as a community. And you can see the decrease in peak is pretty significant. And so this is an example. So this is an example for one home to show the overall results for not for one home. This is for the group of homes for one day. So to show the overall results for a couple of days is shown here. So we had complete data. There were 11 consecutive days that all houses had complete data that could be used for comparison. So this table shows the comparison of the measured energy use in the base case compared with the simulated minimum peak control scheme, so the min peak case right here. So in general, the min peak simulation consumes less energy than the base case, which you would normally think that if you pre-cool the home, you're losing some energy to just losing that heat or that cooling through the house. However, so this comparison might actually be a little bit different, because in the min peak case we were operating at thermal comfort bounds, whereas in the base case that's just what was happening. However, I think understanding the potential of savings if you were to operate not only at those bounds but employ some sort of control scheme is still valid. So while maybe the savings in terms of total AC energy may be debatable just because of that maybe stretched comparison, I think the greatest benefit is looking at the ability of the controller to minimize the peak. So, and that's seen in the savings over here. So savings meaning how large of a reduction there was between the base case and the min peak. And you can see that there's pretty substantial savings, especially if we consider what Con Edison was willing to pay just to shift by 1 kilowatt hour. So the average savings throughout the 11 days for these 41 homes was about 27%. So this highlights the benefits of the centralized controller to be able to leverage the thermal mass of each house, which not only resulted in some sort of cut to the total AC energy, but a significant cut to the peak power place. So the centralized controller is thus able to use thermostat control to be able to shift when each house is using free cooling, and from that you're able to stagger when units are turning on or you're consuming a lot of energy. So you're able to therefore level the load a little bit. So we saw in that earlier graph how the load was a little bit more spread out and flattened, which is a lot easier to deal with for utilities than trying to find additional capacity and buying off of the electricity market just during peak hours.
So Christian, I just had a quick question about this. How much is this savings dependent on an accurate weather forecast?
So let's see. So generally speaking, weather data for the next 24 hours tends to be pretty accurate, just from what I've read in terms of temperature. But we're still looking into ways of doing that uncertainty analysis in terms of savings. So I guess the answer is I don't quite know yet.
Okay, great. And I think that's been one of the the points of discussion or criticism on some of the work in the past regarding energy storage. And we always assume a perfect forecast, but I think one of the things that you just said is maybe it's only 24 hours that's significant, and what you said is the weather forecast for 24 hours continues to improve in terms of the uncertainty regarding that temperature profile. Is that a fair assessment?
Yeah, I would say so. And I definitely think there's room to add that in, maybe as some sort of disturbance. But from the papers I've read, yeah, I mean, it's the same assumption of perfect weather data. I think the problem comes more with when you start to incorporate things like solar panels, especially because it's hard to predict clouds coming through.
Yeah, great.
All right. So in summary, just we were able to show how we were able to use smart meter data to be able to use reduced order models for these 41 homes, and we were able to show a fairly high level of accuracy. And from there, we were able to take this and at a community level implement an FPC scheme for those 41 homes. And from that, we were able to, on average, lower the peak load by about 27%, or about 15 kilowatt hours, without really significant increases over electricity consumption. I'd just like to acknowledge the help that I've gotten from my group, both the Edgar and Valdez groups, and in particular one individual, Wesley Cole, who recently graduated, but he definitely served as a great mentor during this project, as well as Dr. Novoselic, who helped with the building models a little bit, and then, of course, NSF, and then the Palm Street Research Institute for access to their data. With that, that ends my presentation.
Okay, great. Well, thank you, Christian, for the presentation, and I thought it was very excellent. So let's go and open it up for some questions. And what I'd ask is just that you unmute your microphone, to ask a question, or feel free to just unmute it now anyway. I'll go ahead and just go through and unmute microphones, any that are giving a lot of feedback. Then we can go ahead and mute them again. But feel free to ask a question in the chat window, or just go ahead and ask a question via the audio. So we'll go ahead and turn it over now for any questions that you might have. So John Sorolla and I were talking just in England at the conference. John, do you want to tell them a little bit about your issue with your home and how much extra electricity you're producing from your solar panels?
Oh, that was just an issue of we missized the system because of conservatism from the point of view of the installer, since they guarantee a certain production. The system is oversized. Yeah, so in that particular case, our system ended up being about oversized by 20%, and then we changed our electric load, which didn't help any. But I don't know necessarily, John, what you want me to say to that, though.
Well, I was just wondering, do you guys have time of day pricing? And I just wonder what kind of, I know you've been thinking of some of these things, and is there any kind of energy storage that you could use at a home level to take advantage of time of day pricing?
So we actually do not have time of day pricing. It's an option, but it makes almost no sense for anybody in New Mexico because the swings are strange, and the peak, their only time of day pricing right now that our local utility provides is a diurnal swing. That is, it's cheap between about midnight and 6 a.m. and it's unearthly expensive between 6 a.m. and midnight. Like factor of 4 difference. So and the daytime pricing is more than twice what you pay on a flat rate. So it doesn't make any sense. But that doesn't mean things won't change. The other strange thing is New Mexico's in a different sense. I was talking to Tom about this maybe a year ago, that peak shaving is not as big of a deal for us. It's a lot bigger deal for Texas, but on our portion of the grid, peak shaving's not the problem. Their problems are starting to come in more in the dynamics of having too much wind and solar for the size of the grid, and that's starting to make control, because they don't have enough natural gas, and Texas has a lot more natural gas. So our issues in New Mexico are far more related to dynamics. At least that's the way I understand it.
So try and make it like a leveled load instead of just kind of more constant than anything.
Yeah, so if you're going to do renewables, right, the first thing you have to do is build a natural gas plant to back it up. Because which has recently become a big criticism of high PV panels, insulation, and stuff like that. Yep.
And you can't depend on it all the time.
That's right. And whereas Texas actually has a fair amount of installed natural gas capacity, I had the opportunity to chat with the guys in ERCOT once, and they kind of gave the same impression that dynamics were not their concern. So they weren't worried about, drop off the wind or a cloud running over a PV facility. Whereas for a place like California, or a place like, even to a certain extent here, where we have less, a lower percentage of natural gas generation, a lot more of our power comes from coal, and coal has a lot harder time with all of the noise injected by the renewables. So for us, it's this, it's trying to get something that looks more dispatchable would make them a lot happier, as opposed to just shaving the peak.
Yeah, which I think
it's a difference. It's that we have a different installed generating mix. So everybody has their crisis of the day, right? And my impression, and I'm not intimately involved in this, so this is more impressions, and I'm not speaking from any point of authority. But my impression is that the dynamics are a bigger concern right now than peak. Today, who knows about tomorrow?
Yeah, I think part of what you said highlights, I mean, utilities have different incentives for what they want to accomplish, but they also have the money to be able to do it. So there have been a lot of examples of successful, like, peak shaving techniques that have been used by utilities. So there's I have shown an example of centralized control, but I think decentralized could be done in a way, but it would require, like, utilities to provide some sort of incentive for you to participate in that kind of thing.
Oh yeah, no, I mean, this isn't a criticism. This is just answering John's point that my particular situation is different, but
yeah,
absolutely, this is good stuff.
Okay, great. Let me go on to the next question on the chat window. Dr. Paquette at RPI had a question. Actually, this is from somebody else who's participating with them, Matt Titus at RPI. Do you have any sense of how well this approach might scale? For instance, can you optimize over thousands or millions of customers in real time, given computational and or IT infrastructure constraints?
Let's see. I feel like the computational power, the optimization scheme runs in seconds, as it is right now for all the homes for the 11 days. But I mean, I'm always trying to get more data to be able to evaluate that. I think more and more. I think, like, the idea of neighborhoods being able to act as, be able to have, like, distributed energy and stuff like that. I think that's more how utilities would actually implement it. Look at, like, just try and get neighborhoods overall to be able to level their load. But I think that's a valid point and something that I should think about in the future. But I do know that, for example, especially with smart thermostats being installed, Nest has done like a pretty cool thing. You might want to look it up. It's like called, I think it's called Nest Rush Hour. And it's a way of they've used some ideas behind this with pre-cooling homes, and they've been able to implement it. I think it was in England and maybe somewhere else in the United States. So that's one example where it's been implemented. Usually, for well, as far as I've known, in terms of utilities, like a couple of ways that they've tried to lower peak demand has not been terribly efficient. So one way that they'll do it is you get into this like buy-in program. And basically what they do is during like 5 events during a year, they'll shoot out this giant radio blast that'll turn off the compressor in your HVAC system. And so it's not very accurate because it's kind of like a giant widespread blast to turn off like compressors. So I think maybe with smart thermostats and smart appliances, there might be, especially if it's already installed within homes, there might be an easier way to be able to like actually implement something like this. But I do think that's something I should think about.
Okay, so Matt just chatted in the window. It's called Rush Hour Rewards, and then the NIST Airwave. So 2 things that are current programs. Sounds like the coordinated approach is, where you have some centralized control. Like you said, that might hold the most possibility for levelizing or implementing this on a large scale. So anyway, he says thanks for the response. So great question, Matt at RPI. Okay, so any other questions from the audience here?
Yes, Christian, I have a question. Can you hear me?
Yes.
Right, Christian, this is Pablo from PSE. I wanted to ask you, is there have you seen because you showed the aggregate numbers, so were all houses having a smaller energy consumption, or was it that just 1 or 2 houses were the most determining factor there in reducing the shading of the peak, and all the others didn't change much? So what's the spread essentially?
That's a good question. So I think the first one you asked is if they use the same amount of energy. The answer is no. Like in this kind of scheme, I don't think losers is the right term, but there will be people who use a little bit more energy because you are pre-cooling a home. But there's a definite difference between homes that, like, you can visually see that they have a thin building envelope because they always have to operate at the bounds compared to others. So if this were to be implemented, there would have to be some sort of incentive so that, you as a customer, well, let's see, so the overall idea of this control is, can I get users to still feel the same comfort thermally? Like, you come home and you don't notice, like, your house is still cool, and you're maybe paying less money for electricity.
Mm-hmm.
So I think because definitely different homes have different efficiencies in thermal mass, there would have to be some sort of way to be able to mitigate that, maybe in terms of like payment for inclusion in this program, or some sort of credit to be included in this program, because not all homes are benefiting in the same way, but overall as a community there is a leveling of the load.
Very good, excellent. Thanks for your answer. So how do you see that? I mean, how does it come up in the model? Is there a concept of gains or something like that, or is it dynamics? Is it something that's straightforward to see or characterize?
It might be seen because the model is acting at hourly intervals. It's hard to say that it's exactly dynamic, but it has to do with this, let me think, sorry. I have to say this clearly. It more has to do with the size of the coefficients that are regressed from the reduced order model, and we're still working through. Because one benefit we see in this research and that we'd like to see is to be able to not only identify homes, but in sort of like an error detection way, be able to suggest, like, it looks like the insulation of your home is very thin.
Correct.
And so we'd like to be able to recommend that you increase your insulation, and if you were utilities, they're already doing programs where they'll like install a thermostat or increase the insulation in your home. So if your utilities company that you're already going to, says, hey, we will install insulation in your home at no cost, then this data can be used successfully in some sort of like error detection or retrograde suggestion kind of way. So we're still working through that idea.
Terrific, very good.
All right, excellent. Krish, I just had one other question for you, and maybe this is just an idea that that might be worthwhile to look into. Is that, you know, one of the complaints, I think John Cirola brought this up in his comment, is just the intermittent nature of and the dynamics of the energy availability versus energy consumption, especially with renewables, is problematic. It seems like this would be a great candidate. You know, thermal storage within homes would be a great candidate for something like photovoltaics, where, you know, if the sun is out, then you're likely going to need more air conditioning or more cooling load on the home, versus if it's cloudy, you need less energy. And so it almost seems like this would be a great candidate to couple with some of the solar work that's going on with you know, the photovoltaic. So any thoughts about that, on how to maybe deal with some of the intermittency issues?
I think that's a great point, and a good thing for me to definitely look into in the future. I think so. Wesley Cole did some previous research looking at community thermostat control as well. He did it using Energy Plus models, and he just used like an average PV load. And what he found is that homes will shift they will try and minimize peak at the same time if they're affected by PV panels, because whether acting as individually or at the community level, like the load, if they want to lower their own load, then they kind of do it at the same time as if they were in a centralized controller. But I don't think we've as a research group, dealt with the intermittency yet. So I think that would be definitely something worthwhile to look into. Like, what happens if a cloud comes or something like that? How would your control change? So yeah, it's definitely something I'd like to look into.
Okay, great. Okay, any last questions from the group?
John, if I could follow up on that. That is actually something that would be really cool, because one of the things that we do have here is a program where the utility will, it's not as clever as smart metering, but they will shut off your air conditioning, because that's one of our biggest electrical loads in the desert. They'll shut off your air conditioning to manage dynamics in the network. And while I haven't participated in this, some of my neighbors have, and their experience has been not at all, well, not 100% positive, because the utility doesn't know anything about the state of their particular building envelope. And this would be a really interesting way to play, to allow the utility to know a little extra information about the state of the various homes envelopes when they're deciding which homes to basically curtail air conditioning on to manage some of these dynamic problems. Interesting.
Yeah. So you're saying have light meters or temperature sensing within the home before they just, you know, automatically cut off your air conditioning.
Well, these reduced order models could be equally useful to a utility deciding how to manage their. They're trying to do a dumb version of smart metering, right? Instead of the individuals deciding to curtail their air conditioning load, they're coming down and saying the following air conditioners will be turned off. Okay, it's entirely centralized from their standpoint, and the consumer actually doesn't have any control, which leads to consumers that are less than pleased. But you could easily see where they could mitigate some of those problems if they had their own reduced order models of the individual building envelopes to provide them extra information to effectively do a lot of the same kind of control schemes, but from their side instead of from the individual home side. Does that make any sense?
Yeah, no, that makes a lot of sense.
Yeah, so if you could identify homes that have thick thermal masses or something like that. So if you do turn off their air conditioning, they don't really notice. So their like customer satisfaction is pretty high because they can't tell the difference. Something like that.
Yeah. Yeah. I mean, you know, I think that would be a really cool direction to take this as well. So.
All right. I appreciate the feedback. I'll definitely take a look at that.
Okay, great. Okay, well, great. Thanks everybody for the questions. We'll go ahead and wrap it up now. And Christian, thanks again for the presentation. I thought that was excellent. So